Okay, so in this video, we're going to be going through the process for finding all the zeros of a polynomial using whatever tricks we have available to us. So I have a 5-degree polynomial, 5th-degree polynomial, so it has 5 zeros. Some of them could be complex. At least one of them must be real because it's an odd degree polynomial. So it has to go from negative infinity to positive infinity, and so it's got to go through zero someplace. But it could have more real zeros, but it has to have at least one to get us started. So the first thing that we're going to look for, besides just the total number that we need to find, is we're going to apply some of our theorems and see where we can begin. So I'm going to start with the rational zeros theorem. Now, the rational zeros theorem, in this case, since the leading coefficient is 1, is just going to be the factors are going to come entirely from the constant at the end. So plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 4, plus and minus 6, and plus and minus 12. So those are the only possibilities for rational zeros. So that's something that we can try. We could also look at the rule of signs. Let's see, we've got one sign change, then there's a second sign change, then a third sign change, and then a fourth sign change. So it could have 4 or 2 or 0 positive zeros, and therefore at most, just by virtue of definition, maybe 1 negative. So let's try p of negative x. We would flip the 5th degree, then that one stays, this one flips, that one stays, that one flips, that one stays. So we have only one sign change, negative, negative, and then it flips to positive. So one possible negative 0. So those are our only options. So since there are more positive zeros than negative zeros, I'm going to start by doing my division. I'm going to start with the positive zeros, 1, 2, 3, 4, and see, hopefully I'll hit on something, and then it will reduce my problem, and then we can reassess. So I'm going to do synthetic division since, again, with practice, that'll be a little bit faster than doing long division. It will certainly take up less space. So I'm going to insert a place to draw, and we're going to start with our coefficients with the original polynomial, 1, negative 1, negative 7, 11, negative 8, and 12. And if I start with 1, then the factor would be x minus 1, and the 0 would be 1. So 1 goes in our synthetic division. And we bring down the 1, we multiply 1 by 1. And then I multiply 0, I get negative 7. I multiply, I get negative 7. That gives me 4. That gives me 4. That gives me negative 4. That gives me negative 4. And that gives me 8. That's not 0, so that doesn't work. So I'll go on to 2. So put a big X there. 1, negative 1, negative 7, 11, negative 8, and 12. We'll try the 2. Bring down the, oops, that deleted too much. Try again. Not a lot of space to draw, but we bring down the 1. I almost did it again. Multiply, then I get 1. Then I multiply, and I get, that gives me -5. And I multiply, that gives me -10, which gives me a 1. I multiply, that gives me a 2, -6. I multiply, that gives me -12, and adding gives me 0. So there we go. I found 1. So the first 0 I found is x equals 2. So the factor is x minus 2. And right now, what I have is p of x is equal to x minus 2 times the polynomial that's left is 1 degree smaller. All right, so now that I've found a 0, I can reassess. So possible rational zeros of the quartic factor that remain are going to be plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6. So I don't have to worry about 12 anymore. That's eliminated. And in principle, I already tried 1. And if 1 wasn't a factor of the whole thing, it's not going to be a factor of the new thing. So I can also eliminate 1. I can't necessarily eliminate -1, but I can eliminate 1 because I've already tried it. So I'm going to try starting with 2 again. Now the thing is, 2 is still a factor here. And so there could be a second factor of 2. And so even though I found it 1 time, I should try it 1 more time in case it is a repeated root. So we're going to put in another place to draw. And let's continue. So 1, 1, -5, 1, and -6. And I'll just scroll back up just to double check. 1, 1, -5, 1, and -6, just in case I screwed up someplace. And we'll try 2 again. So bring down the 1. 2 times 1 is 2. That'll leave me with a 3. That gives me a 6. That gives me a 1. That gives me a 2. That gives me a 3. That gives me a 6. And that gives me a 0. So that is a remainder. So I did have an extra factor of 2. And so now I can write p of x as x minus 2 squared, since I have 2 factors of x minus 2. And what's left is 1 degree less than the previous step, x cubed plus 3x squared plus x plus 3. Now at this stage, I've got to a cubic. So one thing that I might be able to do is consider factoring by grouping. It's going to depend on the specific problem. Or you can keep trying other values. We found 2 positive zeros. There could be more. There could also be a -0. But in this particular case, since I can actually see with my own eyes that this in fact can be factored by grouping, that's what I'm going to do. So I'm just going to take the cubic, x cubed plus 3x squared plus x plus 3. I can take out x squared from the first 2 terms. And from the second 2 terms, they only have a 1 in common, which is going to leave me with x squared plus 1 and x plus 3. And so my final factoring version, fully factored version, is x minus 2 squared times x plus 3. There's my negative 0, and x squared plus 1 turns out to be complex. So my zeros are x equals 2 with multiplicity 2, x equals minus 3 with multiplicity 1, x equals I and minus I with multiplicity 1 each. So now I could go ahead and I could graph my polynomial, and we'll just sketch it, and then we'll check Desmos for confirmation. So we're going to end up with one, two, going to be there, 1, 2, 3. We're going to have a 0 there. These don't contribute any zeros. This is an odd polynomial. So, and it has a leading coefficient that's positive. So it's going to have to start down here. This is a multiplicity 1. So it's going to go through, and it's going to go up to our y-intercept of 12. And then it's going to come back down. It's going to touch the graph at x equals 2 because it's multiplicity 2. It's not going to go through. It's going to bounce off of it. And then it's going to go up to probably more steeply than this, but it's going to go up to positive infinity. And so let's check Desmos and verify that this is in fact what happens. And our graph ends up looking like so. Now we have no way of knowing without doing a lot more like calculus and things, or like guessing and plotting some extra points exactly where this peak is at. But this kink in the graph here comes from the complex roots, but we can see that we have at x minus 3, x equals minus 3, we have this graph going straight through the axis, and then at x equals 2, it bounces off before heading off to infinity, and we do have an x-intercept at 12.